Here we're going to look at an energy balance that includes radiation. So our overall energy balance is equal to the rate of energy in minus the rate of energy out plus the energy that is generated, and that's going to be equal to the rate of energy that's stored. However, here we are only going to look at steady state, one-dimensional heat transfer with no generation. So our energy balance is going to simplify to basically that E in is equal to E out. So a couple of things I want to mention. These dots here mean that it is a rate of heat transfer, and this double prime here means that we're dealing in watts per meter squared. So the first thing you should do when you're doing an energy balance is draw the picture. And we're going to look at a classic example, which is a horizontal plate. It has a constant surface temperature, Ts, and is exposed to airflow on both sides at a temperature of T infinity, where T infinity is going to be less than the surface temperature. So let's start with convection. So if there is a fluid next to the plate and a temperature difference between the plate and the surrounding fluid, there is convection. It could be negligible, it could be forced or free, but if there is a temperature difference, we use Newton's law of cooling such that Q, convection, is equal to H, which is the convective heat transfer coefficient, Ts minus T infinity. And here, since the plate is exposed to fluid on both sides, and we're going to assume that H is constant, our total convection is going to be equal to 2 times H Ts minus T infinity. So now let's look at the radiation. Is there radiation? The answer is yes. There's always radiation if there is a temperature difference. In fact, radiation is the only mode of heat transfer that can occur in a vacuum. So there are two terms that are important for radiation. The first is this G, which is known as irradiation, and J, which is radiosity. So G is all the radiation incident on the surface, and J is all the radiation leaving the surface. So what happens is this is the G that is coming in, and here's the J that's leaving the surface. Remember that this is only the radiative heat transfer. So our energy balance ends up being 2G is equal to 2 times J plus 2 times our Q convective, and we divide everything by 2, so G is equal to J plus our Q convection. However, we can make this a little clearer. So irradiation, this G, can be absorbed, transmitted, or reflected. So this would be alpha G plus rho G plus tau G. And as you can see, this also means alpha plus rho plus tau is going to be equal to 1. So J consists of the radiation emitted by the surface, E, or emissive power, plus the irradiation that's reflected from the surface. So now we can write that G is equal to E plus rho G plus Q convection. And if we call the surface opaque, there's no transmission, so tau is equal to 0. And now we can write that G equals E plus 1 minus alpha G plus our Q convection. So the surrounding fluid can be treated as a black body since it's large with respect to our plate. So that means that our irradiation is equal to sigma T infinity to the fourth, where our sigma is the Stefan-Boltzmann constant, which is equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. E is equal to the emissivity times the radiation of a black body, which is sigma T, now this is T of the surface to the fourth. Note that this is almost identical to that of the irradiation, except the temperature is always that of where the radiation is coming from. And very important, all the temperatures must be in Kelvin. So finally, let's write this out in terms of temperatures. So we have that sigma T infinity to the fourth is equal to epsilon sigma T S, T of the surface to the fourth, plus 1 minus alpha sigma T infinity to the fourth, plus H T S minus T infinity, or simplify it even further, alpha sigma T infinity to the fourth is equal to epsilon sigma T S to the fourth plus H T S minus T infinity. So this equation assumes that all the radiation comes from the surrounding fluid. That's not always the case. Often the plate will be in a large enclosure, such as a furnace at a different temperature, and we indicate that temperature as T of the wall, sometimes T of a furnace, and that can be greater than that of the plate. Therefore, you need to include the irradiation from there as well. Again, because we consider it to be a small object in the large enclosure, the walls of the enclosure, GW, that irradiation, is equal to sigma T of the wall to the fourth. So this is treated similarly as the irradiation from the surrounding fluid, except with a different temperature. So now our final equation can be alpha sigma T infinity to the fourth plus alpha, now this is the alpha of the wall, sigma T of the wall to the fourth, and that's going to be equal to epsilon sigma Ts to the fourth. So that's your emissive power plus HTS minus T infinity. One thing to keep in mind is that the alphas are not necessarily equal, and in fact are often not. So along with the question stated before, try to simplify or complicate things by asking yourself, is the surface opaque? So if the surface is opaque, then tau is going to be equal to 0. Is there irradiation from somewhere else besides the surroundings? If so, again, if you have an object placed in a large furnace where those walls can be considered irradiating, you need to include that in your energy balance. And take a look at what's given. Is the radiosity given? Use that number. Is the irradiation given? So use that number instead of trying to calculate it. Another thing is you might be asked to find this convective heat transfer coefficient, and to do so you may be using a Rayleigh number correlation, or you'll need to find the Nusselt number. So make sure you know the geometry, what type of convection is, and what the flow regime is. And finally, you might be asked to find the surface temperature of the plate. This is going to require some kind of solver, as the temperature appears as both T of the surface and T of the surface to the fourth. In that case, all temperatures must be, even that in convection, used in Kelvin.